Yeah, so I just need to click. Now we're doing it all wireless. But wasn't the problem with the cake? I don't know what the problem is. Something didn't work. So instead of giving you all epilepsy, we opted for this solution because otherwise everything was blinking constantly. All right. So hi everybody. So my name is Jarle Brinchmann. I'm a Norwegian astronomer working in Portugal. The only one, not surprisingly. There's not a lot of Norwegian astronomers anyway. I'm currently director of the Center for Astrophysics at the University of Porto. I've been around a bit. I did my PhD in England, so overlapping with Carlos. We were in the same place actually at the same time. And then I was a postdoc in Oxford and Munich. And then I was here for a while, and I was 10 years in the Netherlands as a professor at the University of Leiden. And that's one of the places I got involved in this mission that I'll talk about. I don't know if it's an idea to reduce the light a bit in the room, if that's possible, because that's on my side. Ooh, okay. Okay, it's digital. Okay, let's see if I can keep you awake for 20 minutes. Right. Okay, so before I really get into the mission, I want to take you a little bit of a step back and think about, the way we look at the cosmos. When you go outside and you look at the fantastic celestial sky, like in this case from Paranal in Chile, there are questions that humans have asked themselves for immemorial times, such as what does the universe contain? Obviously, slightly different words in the Iron Age. Where does that universe come from? And what does the future of the universe look like? Those are all questions that we have asked ourselves for a very, very long time. And we still continue to ask ourselves those questions. We refined the way we ask them. We got different set of tools for actually answering them. But they are fundamental. And that has meant that cosmology, the study of the heavens, has a very long human history. Goes from perhaps some of the earliest recorded evidence we have is the Nebra sky disk, which you see here, which is from 1600 or so before Christ. And that comes from a period in the Bronze Age where cosmos was relatively nearby. There were things like sun, the moon, trees, animals, etc., things close to you. And then as we moved on. I'm following here the sort of Western historical arc. So going to the Greeks as the next one, where everything became systematized. It was perfection, spheres, circles, everything was nice, geometric solutions. The textbook by Aristotle, the Caello, was probably the cosmological textbook that has been used the longest in history. So like almost 2,000 years. And this evolved very slowly, even all the way through the Middle Ages and Renaissance. The main difference was that everything became much more religious and became the divine cosmos. Everything was again perfection. Perfection was identical to divinity. And the real change, and what really makes us sit here today, came to a large extent due to Isaac Newton and a few people around him, which really realized that. And this is the fundamental insight. It's not something that's trivial. It's not something we usually talk about when we teach this, but it is really very profound, is that the universe can be described by physical laws, right? Before then, often things it happened. Right? It happened because of divine contributions here or there, and things just changed. Now, you suddenly had a system to understand the universe by, and not only that, you also had a language that you could use, and that language being mathematics, right? So mathematics became then the language instead of English or Latin or Greek or whatever, or Chinese for describing the universe. And this then led to a rapid evolution in the ability of our ability to study the cosmos and to ask questions about it. And so here is a very short timeline of the last 150 or so years, which sought to establish what's the state of the universe. And that's where we then going to get into Euclid. And so if you go back to sort of around 1900 or so, there's a lot of very famous people, all whose names you probably know, people like Poincaré, it's Kelvin, Kapteyn, Oort. They studied the dynamics of stars around us because they were interested to know if what they saw was everything there was. Right? That was a logical question to ask at the time. And so they were looking for what they called dark matter. And they found at the time that around the sun, there isn't a lot of dark matter. But move forward about 30 years, there's a Swiss astronomer, Zwicky, who instead of looking at stars just next to us, he started looking at galaxies and how galaxies move in a galaxy cluster. And he found that indeed in these big systems, there was a lot of dark matter, a lot of matter that he couldn't see. So much more than he could see. And that was, of course, controversial and surprising, but it was certainly got also plenty of interest. In parallel, there was a bunch of guys, and there were always guys at the time, because they were the only ones that were considered to be reliable enough to get access to telescopes. So these are Slipher, Lemaitre, and Hubble. Not that you can recognize it with this resolution, but you can on my screen. So. And they found that the universe was expanding, and that was a real shock, real surprise, right? Why was the universe was no longer static? That old Aristotelian idea just disappeared. And so along that period, there was more studies of galaxies, more studies of rotational galaxies, which today is more the textbook. We see that stars in the outskirts of the galaxies are gas, rotates much faster than it should, based on just the stars inside, which again leads us to conclude that there is a lot of dark matter. But up until this period, this was sort of late 60s, early 70s. If you look at the papers from that time, people were saying, well, like this might be like tiny stars, dark stars, things that fly around that we don't see, but are just very, very low luminosity. But what happened then in the 80s, into the early 90s, was that there was a combination of theoretical work on understanding the nucleosynthesis or the origin of the elements in the universe, and observations of the cosmic microwave background that taken together implied that there was no way that this dark matter could be made of baryons, or the kind of matter that we consist of. Let me just get rid of this. And that's also a very fundamental thing, right? There is a lot of stuff out there, and it's not what we are thinking. At the same time, people were continuing to study the acceleration and the expansion of the universe, and they started studying, particularly in the mid-90s, there were many studies using supernova, trying to understand how the universe was expanding. And the surprising conclusion of all that was that it wasn't just expanding, the rate of expansion was accelerating. It was blowing up. Right? There was always a possibility, but it was always, for a long time, was considered a bit of an esoteric possibility. And this rather shocking discovery earned the leaders of this supernova, with those pixelated guys over there, they earned them the Nobel Prize in 2011. Well, so this has all led us to what's sometimes called the pizza nobody ordered, which is basically, you can see the recipe on that slide if you want to make a universe. It's mostly dark energy. And the premise has told you lots about how you can, what you can do beyond the standard cosmological model. I'm not going to talk about that. But in the standard model, what we interpret is there's a lot of dark energy, which we don't know what is, a lot of dark matter, which we don't know what is, and then there's a little bit, like 4%, that we know what is. And that's really, I mean, it's a relatively robust result. I think we are confident in what we get out. But it's very unsatisfying that most of the universe is stuff that we don't know. And so that is where we would like to make progress. And to make progress on that, we want to understand better the expansion of the universe and the growth of structure in the universe. And so I said already that the universe has been found to be expanding. And the fundamental law that Hubble and the method found was that the speed at which galaxies go away from us is proportional to the distance from us. Okay? The speed is easy to measure. The distance may or may not be easy to measure, but what has changed in the intervening years, so this is still true at very, very close to us. What has changed is that we now understand this better. This constant is not a constant, it's a function. But we can still use something like this to measure a speed and infer a distance. And as I'll show later, this is actually quite important for Euclid. But all this taken together has led us to this picture of a cold dark matter universe, where the you can see in the background that's result from a simulation. I'll show you the video in a second. And all the black is dark matter, and all the yellow is stars. And you see that most of the dark matter is clumped. Okay, it's just gravitational attraction that clumps it. And so the universe is built up of building blocks that we call dark matter halos. And these sort of hang together in a filamentary structure called cosmic web, and galaxies live within these dark matter halos. And this is a very successful theory. Here's a movie of a forming universe where dark matter is black and stars are yellow. And you can see as gravity acts, gravity causes things to collapse together. And you would naturally have first into sheets and into filaments, and then eventually into clumps. And that's what you see building up slowly but surely. And these kind of models, these kind of simulations are super successful. But they rely on a lot of ingredients that we don't know. And there are many, many ingredients we don't know. So here, but today I'm just going to mention very briefly the cosmological ingredients, because we have to say something about cosmology when you make a simulation like this. But it actually doesn't matter very much. It's not terribly sensitive to the cosmology that you put in. And that is one of the challenges. If you want to learn more about dark energy and dark matter, right? Now we're going to talk about how do you design a survey to do this. Okay, the first challenge is that the effect of dark energy is very, very subtle. So here's a snapshot of some simulations where there are different models. They are not all about different dark energy. It doesn't really matter. The different cosmological models. Here, these are simulations that started the same way. They started down here, and then this is far back in time, closer and closer, and this is the present day at the top. Okay, so now if you compare the various columns, you see that there's actually not a lot of difference in this distribution of particles. There are some cyclones, but they're very small. So this is one of the challenges when you want to study the effect of dark energy or study cosmology, is that there isn't a very strong signal. Right? It's not something that shouts at you from the universe, will shout at you and say, oh, look at me, I am this cosmology, right? There's a small effect. So that leads us to having three consequences. And that is that, we need to have, is what I should say in the first one there, we need to have very precise measurements. And we need very accurate measurements. Hopefully you know the difference. And we need cross-checks, right? And so just to illustrate this difference of precise and accurate, in this case, you can imagine I wanted to measure the average height of all women in the world. And I go to the Netherlands and I measure the average height of all the women there by a sample of 1 million females. And I get a very precise measurement, but it's not going to be corresponding to the reality of the whole world at all, because the Dutch are on average much taller than everybody else. So if I wanted a very accurate measurement, I would need to measure from spread over the whole planet. And equally important, we need cross-checks, because I might have some method that works, but I made a small mistake, and then I don't know. But if I had another measurement made in a different way, I can cross-check them and see if I get consistent results. So that's one thing we really want in order to design a mission to really learn about dark energy. So in practice, that means that we need large surveys to get precise measurements. We need to really control the survey. So this mission, which I'll say more about it in a bit, is a long period. Making a space mission takes typically 20 years. That's sort of the ballpark figure. It can take 5 or 10 more. It can take maybe 5 years less. But you need that to really understand everything you're doing in the process. And to get cross-checks, we also need multiple probes. But finally, there is another challenge in the whole thing, which we also need to be aware of. It might be that the theory of gravity that we have, and that you spend plenty of time during this AstroCamp to learn, may be completely wrong, right? And all your work has been wasted. Well, obviously it works extremely well, right? So, so there's no problem with the current theory of gravity if you want to fly to Pluto. But we always need to keep our mind open about the possible changes to even to a theory of gravity. And so in order to do that, you want to do something that's flexible, that you can change things around, that's not tied to one particular way of doing things. So the techniques that usually are used in cosmology can fall into 3 different camps. The 2 have to do with distance measurements. So you can look at the star, and then you put it at twice the distance, it becomes a quarter of the brightness. You put it at 4 times the distance, it becomes a 16th of the brightness. Or you can do the same thing with size. Again, you put it at twice the distance, it becomes like smaller, 4 to the distance, smaller again. And the interesting thing is that the distance you infer from these 2 methods in general relativity, they're different, right? They're not the same. It's the angular, this is the luminosity distance, and this is the angular diameter distance. In Euclid, we're going to use this one. So these 2 methods, you can use them if you know something is the same brightness everywhere, or you can kind of correct so it always has the same brightness, then you can use this technique. That's what people have done with supernovae. It's been extremely successful. If on the other hand, you know that the size is the same, then you can use this technique. And that's what Euclid is going to use. We're going to use something called, which is a fixed ruler, using a technique called baryonic acoustic oscillations. It's a bit fiddly to go into the details of how that all works, but I can show this very simplistic video. So early in the universe, there will be these sort of sound waves set up. And these sound waves move out, they cross, but they will have a characteristic scale. And these waves will sort of push material with them and cause slightly more material at certain distances apart. And what that leads to is if I now show you a plot that has distance between galaxies. So what's the chance, if I'm standing here, what's the chance of having a galaxy here? Right? So what's the chance, if I'm in the Milky Way, what's the chance of having a galaxy 100 kiloparsec away? That's actually quite high. But if you ask me, what's the chance of having a galaxy 150 megaparsec away, it's usually quite low. And we can calculate what this looks like. And I could even show you this. If I could get this to work. Oh, here we go. And what happens is that these acoustic oscillations, they make it slightly more likely to have a galaxy in the vicinity of this kind of distance, which sort of 150 megaparsec distance. And we can use that as a way of measuring. There's a fixed scale in the universe, and we can use that, and that scale exists in the sky, and we can use that to measure distances to things. And we can constrain cosmology that way. So that's one way, but we wanted to have multiple ways. And so the other thing we would like to do is measure how things grow in the universe, right? So gravity is the force in the universe. It makes things grow, makes things form. So we would like to have something that can trace gravity and trace the growth of galaxies, growth of structure of the universe. And so what we really need is to weigh the universe. And that's, of course, always a challenging thing, because you can't go out with a balance and put a bit of universe here and then do that. But so the technique we're going to use is gravitational lensing. So that's the fact that when light goes past the mass, it will bend slightly, right? It doesn't bend a lot around me, but around the sun, there is a very slight bending of light around the sun, which was the famous confirmation of the theory of gravity. And we know that that works even better on large scales in the universe. And so, and here is a very spectacular example of this. You can see here in the image here. No, you can kind of see. Okay, the top right, you can see the actual galaxy. And then there is a lensing galaxy that's in the way, in the middle. This galaxy is just behind this one. And the light gets bent around, and it creates what's called an Einstein ring. And that's what you see here. This is a background galaxy that's actually behind this galaxy here, but the light has come around almost perfectly around this foreground galaxy. And so this is called strong gravitational lensing. It's very spectacular. It's fantastic for weighing this galaxy. I can use this to calculate how much this galaxy weighs, but it's totally useless for the universe as a whole, because it happens on small scales. So what we actually need, if you want to weigh the universe, is a weak version of this. And so when there is what we call weak gravitational lensing, the galaxies don't get completely distorted, they get slightly squashed. And they get squashed sort of radially relative to the mass that bends them. And so now if every galaxy in the universe was circular, this would be super trivial to use, because I could just go out and I can just measure what's the ellipticity of every galaxy, and I can find out where all the mass is in the universe. And it doesn't work, because that's not what galaxies look like. So we need to do this statistically. We need to, I can show you, this is the example of a simulation where you take a field of galaxies and then you put the mass in front, and it starts distorting the shapes of the galaxies. And then we need to, since we can't measure this in each galaxy, we have to average them together. And so if you average them all together, we get these kind of patterns here, where the length of the lines, it's the strength of distortion. And you can use that now to figure out where there is mass. Okay, if there wasn't any light here, you could see, oh, there's mass here, here, etc. And this is what we want to measure with Euclid. And so to do this, we need to do two things. One is that we need to do extremely good images. And the other is we need to be able to divide up the universe in multiple slices. And for using that, we will use the Hubble Lemaitre rule. Okay, so let me skip over this one because I'm too late. So Euclid is a satellite with a 1.2 meter mirror. It has a weight of about 2 tons. It was launched 1st of July. It has two main instruments, a visible instrument that you see here, which takes images of a quality comparable to the Hubble Space Telescope. And it has a near-infrared imager here, which are going to take near-infrared images of the sky as well as spectra. If we were to do the same thing from the ground, by the way, it would take about 760 years to do the equivalent to what we're doing in 6 years from space. So that's a bit better. It's a big camera. You see the full moon here. This is the size of the camera on the sky that we're going to use. And it has a field of view about half a square degree. It's the biggest high resolution camera sent up into space that we know of course. Maybe the military has something that's better, but that we don't know. And that's the near infrared image on that side. So this is all sort of what we were planning. I had hoped that perhaps I would be allowed to show some really the first good comparisons, and I'm going to, but I don't have a lot of fancy pictures to show because we're not ready yet. We're still in the testing phase. But here's an illustration of what a galaxy seen from the ground would look like, and the same galaxy with Euclid. So that's the improvement we're doing. And now we can imagine we want to use this to measure the shapes of galaxies and weigh the universe. So here's the actual satellite taken this in February before it was shipped to the US for launch. And so here I can now illustrate quantitatively. So this is the total area covered with high resolution imaging of the sky by the Hubble Space Telescope as a function of time. So you can see it keeps going up, of course, it almost must do. And here's what happens when Euclid will come along. I haven't redone this. I made it for launch in 2021. We launched in 2023. So this is after about a couple of months, right? So suddenly, boom, we're going to cover the sky with high resolution imaging to a scale that we've never seen before, right? We're going to have 1,000 times more of high resolution imaging of the sky. This is going to be the new sort of galaxy Google Maps, if you wish, of the sky. So here's an example. I showed you one of these strong lenses. This was the study of strong lenses in the universe called the SLAC survey, 2010. It has doubled, the number has doubled or so since then. And this is what we will get after 2 months of Euclid, right? And it's going to go on for 6 years. So these rare things are going to be very common. So before I show you some of the first images from it, this is image from the launch, happened 1st of July, went spectacularly well. We were supposed to launch from French Guiana on a Russian launcher, but then that became impossible after the invasion of Ukraine. So we managed to swap quickly to SpaceX and was launching with a Falcon 9. And we're heading to the Sun-Earth Lagrange point 2. 1.5 million kilometers from the Earth, and it got there some point in late July. So on the way there, we also wanted to make sure it was on the way. So people went to the telescope in Hawaii. Here's a zoom in on the images they made. You can see a very slight line here. That's Euclid moving about 1 million kilometers away. It's probably even more striking in this little movie, which you see on the side, where you can probably see Euclid moving quite well. And we have a moth crossing, which was not part of the imaging at the time. There's even a couple of asteroids. There's one down here, moving here, and there's one up in the top as well. So at least Euclid was there. It got there. It's now in an orbit together with the James Webb Space Telescope and the Gaia satellite. You can see the 3 orbits there. They look close, but they're never closer than 100,000 kilometers or so. So they're not going to crash. And these are the first images we got out. We're currently doing what's called commissioning and performance verification, which are the first steps of it. So this is what we released. This is from the visible imager. And this here is from the near infrared imager, 2 different fields of the sky. I think with the resolution of the screen, you're not going to appreciate very much the quality. I'm happy to show you on the screen afterwards. Here is an example that zooms in a little bit to give you a bit more idea of what's happening. What you do see, most likely, these lines here, these little halos here, those are all imperfections that haven't been taken out yet. Okay, because we're just testing the instrument, we haven't removed all the instrument problems. But we can do. I'm happy to tell you what they are in detail, but they're still there, and they will go eventually. So let me close by just showing, because I already ran over time. Let me just close by just showing you a comparison between what we could do, what's the state of the art from the ground in the near infrared, and what we get with Euclid. So on the right, you can see the Euclid image. This is the state of the art survey from the ground at the same wavelength, 2-mass survey. This is the same galaxy, but you can see the richness, and if you see it on the screen, it's much more obvious. This is the deepest we have in these sort of general large areas. So this is really going to make a huge difference. We're going to start proper observing of this now with Euclid in the end of the year, and we start by releasing data next year. And then in 2025, we will start by releasing to the whole world 2,500 square degrees. And then we will continue doing that until a third data release in 2030 or so. So this is probably going to be the Google Google Maps of the sky, if you wish, for the coming decades. There's nothing else that's planned that will replace these high resolution images of the sky that Euclid will give you. So if you continue in astronomy, or if you don't continue in astronomy, but keep following it from afar, this is something that you almost certainly will be the reference. If you want to see, oh, what does that one look like? This is what you probably will be using. So, and of course, at the end of this, we will learn a lot about cosmology. That's why we're doing it. We will learn a lot about how galaxies evolve. We're going to study the solar system, maybe exoplanets. We're going to study stars in our Milky Way, etc. So there's a whole host of things that will come out of this, nothing of which I can cover in full in 20 minutes. So, and I didn't anyway. So thanks a lot.